Um, Usually when you talk about a system administrator's job, there's this like pervasive expectation of pristine, perfectly organized
Oh,
dashboards.
absolutely. The Hollywood version of tech infrastructure.
Right. You picture a massive control room, green lights blinking, and everything neatly categorized into nice little
It
boxes.
looks clean, sterile, and, entirely predictable.
Highly predictable. But then you actually step into the trenches of server logs and raw data dumps, and suddenly those clean UI boxes are just gone.
Yeah, they vanish.
You are staring at a completely unformatted wall of text that is, well, I mean, it's just pure chaos. Millions of lines of system events firing every single second.
It is the absolute definition of a digital haystack. And your job is to find a very small, very sharp needle.
Often while the haystack is actively on fire.
Exactly.
And that is the exact reality we are jumping right into today on this deep dive. We are tackling a high-difficulty data parsing and security challenge drawn from an independent study module.
Right. And just to set the context for you listening, this is strictly an independent project. It's not affiliated with Red Hat in any way.
Yeah, good disclaimer.
But its entire mission is geared toward passing the notoriously grueling RHCSA, the Red Hat Certified System Administrator exam.
Which is no joke.
Not at all. It's a fascinating slice of source material, especially when you consider the framing of it. The certification demands practical, hands-on execution. It's not just multiple choice theory.
You actually have to build and fix things.
Yeah.
And the creator of this module clearly has a sense of humor about that intensity, because the cover art for this is just brilliant.
Oh, the cover art is fantastic.
You have this penguin,
Yeah.
right, the classic Linux mascot, standing in the middle of a high-tech server room. But this penguin means business.
It's wearing a tuxedo.
A full tuxedo, complete with a bow tie. And it's holding a microphone in one flipper and like a sweating icy blue soda can in the other.
It's got this great meta layer to it, too, because the text on the image tells us this content is generated using Gemini Notebook, and it even maps out the curriculum.
Yeah, it says Season 2 equals episodes 26A through 50.
Right, and today we are focusing squarely on episode 39, which is titled Regex File Sorter.
And just hearing that title, Regex File Sorter, tells you immediately that we are moving past, basic observation. We are getting into high-level programmatic control over system data.
We are definitely rolling our sleeves up for this one.
Okay, let's unpack this. If we think about the operational goal of this scenario, you are essentially a digital detective.
I like that analogy.
You arrive at a massively messy crime scene, which is our raw data log. And you need to somehow isolate just the relevant clues, which in this case are the error codes.
Right, just the errors.
Then you have to hand those specific clues over to the right investigating detective, which is a dedicated auditor account. And while you do all of that, you have to make sure the precinct's internal security cameras are fully operational the entire time.
So nobody tampers with the evidence.
Exactly. Mandatory access controls have to be locked down.
That is a highly accurate way to frame it. Because before you can secure any data, you have to deal with the reality of the crime scene itself.
The chaotic raw data.
Right. In this scenario brief, you are tasked with parsing a massive, unformatted, raw text dump of system access logs. And the reason this particular challenge frequently trips up certification candidates is that it demands a seamless synthesis of skills.
You aren't just running one tool in a vacuum.
Exactly. You are chaining a low-level text manipulation with standard file management commands, and you're doing it across tightly isolated user directories.
Right, and the lab setup actually simulates this environment behind the scenes.
Yeah.
Like the root user quietly installs a package called CoreTools.
Just to ensure all the standard GNU tools are available.
Yeah, and then it generates a fake raw access log in a temporary folder, the /tmp directory. And it populates this text file with various HTTP status codes.
So it's simulating web traffic.
Exactly. You've got a flood of standard 200 OK messages
Right.
mixed in with a 404 not found, maybe a 500 internal error, a 403 forbidden, and so
Yeah.
on. But I actually have an issue with that setup. Why simulate the benign traffic at all?
What do you mean?
Well, if our only goal in this exercise is to parse out the errors, why go through the computational overhead of generating a massive file full of success codes Like, why the 200 OKs?
What's fascinating here is that in real-world Linux administration, noise is the default state of existence.
Noise is the default.
Oh. Yeah. If you only ever train on perfectly curated files containing, only the malicious anomalies you want to find, you will completely freeze the moment you hit a production environment.
Because production is basically 99.9% noise.
Exactly. The 200 OK lines are the hay. The 400 and 500 level errors are needles.
Ah, I see.
An administrator's primary job isn't just finding the anomalies. It's aggressively and efficiently filtering out the noise without overloading the system's memory.
That makes sense.
I mean, millions of lines of 200 OK are generated every day on a busy web server. If your parsing strategy involves reading every single line into memory before evaluating it, well, you'll crash your own server just trying to read the log file.
Which naturally brings us to the tools we use to actually slice through that noise.
Mm-hmm.
So we have this chaotic raw log file sitting in the /tm2 directory.
Right.
We need a precise mathematical scalpel to extract exactly the error codes we want without grabbing any of the junk. And the source material points us directly to Objective 1.3, which is grep and regex parsing.
Yes.
Specifically, the command they use is grep-e, then in single quotes, 40 bracket 0 through 9 bracket, pipe 50 bracket 0 through 9 bracket.
Yes, exactly. We are using grep, which is, the quintessential Unix text search utility, but we are enhancing it with that -e flag for extended regular expressions.
Now, anyone studying for the RHCSA knows the basics of regex. They know the pipe is an OR operator and the brackets define a character class.
Right, pretty standard stuff.
So I won't ask you to explain the basic syntax, but I will challenge the tool choice here.
Okay, let's hear it.
Why are we using grep-e at the command line for this?
Yeah.
I mean, if I have a 50 gigabyte log file, wouldn't I use a more advanced text processor like awk? Or better yet, just forward the logs to a dedicated SIM tool like Splunk?
Oh, you absolutely would use a SIM tool in a fully mature, highly funded enterprise environment, no question.
Right.
But what happens when the SIM agent crashes? Or what happens when the network connection to your log aggregator goes down and you have to SSH directly into the failing server to figure out why it's dropping packets?
You're flying blind without the fancy dashboard.
Precisely. You are back in the terminal. And as for grep-e versus awk, it really comes down to computational efficiency.
How so?
Well, grep is written in C and is heavily optimized for one specific thing, which is reading a file line by line and matching finite state automatons. Yeah. It doesn't build complex internal data structures like awk does. When you run that grep-e command looking for a 40 followed by any digit or a 50 followed by any digit, you are telling the regex engine to capture all your 400-level client errors and 500-level server errors in a single pass.
With almost zero memory overhead.
Exactly.
That's ruthless efficiency. I like to think of it as a highly specific VIP bouncer at a club.
A bouncer?
Yeah, like he doesn't stop the line to interview everyone. He just looks at the ID, and if it doesn't start with a 4 or a 5, you aren't getting into the new error logs text file.
That's a great way to look at it. That's exactly what the output redirection does here.
But I do have to push back on the safety of this tool.
Yeah.
Regex is notoriously unforgiving. If you are operating at that speed, couldn't a poorly written pattern, say one that triggers catastrophic backtracking in the regex engine, couldn't that just hang the server entirely?
It definitely could.
Or worse, silently omit vital data.
That is a critical concern, and actually the source module directly addresses it with a specific pro tip.
Oh, they call it out.
Yes. It warns that you must always verify your regex patterns on a subset of data before writing the output to a permanent file or pipeline.
Measure twice, cut once.
Exactly. An incorrect pattern can absolutely silently omit critical data. If your regex misses a specific subset of 500 errors because you forgot to account for a formatting quirk in the log, you might miss the exact breadcrumb that indicates a massive database failure.
Wow.
Yeah, you always test the constraints on a small sample before you let it run across the entire gigabyte file.
Okay, so let's say our regex has done its job safely. We've successfully extracted these highly sensitive error logs into our new error logs text file.
Right.
But now we have a massive architectural problem. That file is currently sitting in the /team folder.
Which is not good.
No, that is a public, world-writable directory. We've just taken a massive, obscure haystack and conveniently concentrated all the valuable threat intelligence into one easy-to-read file.
And left it sitting on a park bench, which is a massive liability. You cannot leave sensitive investigation data in /tm. It needs a highly restricted, permanent home.
Right.
This moves us into the provisioning and file management phase of the scenario, which covers objectives 1.8, 9.1, and 10.4.
So the administrator needs to build a secure containment strategy from scratch.
Based entirely on the principle of least privilege.
Right, so we don't just move the file to the root directory. We create a specific, isolated environment.
First, we create a dedicated user account solely for this purpose using the command user add auditor.
Okay, so we aren't giving these logs to an existing human user.
No, we are creating a dedicated service account. Next, we build the isolated workspace with mudr-p/home/auditor/investigations.
And that -p flag ensures that if the home or auditor directories somehow don't exist, it creates the entire parent path without throwing an error.
Exactly. It's a lifesaver. Then we use the mv command to move the error logs file out of the public/tmp space and into the new investigations directory.
But just moving it isn't enough, right?
No, we have to explicitly lock down the permissions. We use #R, auditor:auditor on that investigations directory.
Now, applying #R recursively changes the ownership of the directory and every single inode inside of it, so that only the auditor user and group own them.
Right.
But here's where it gets really interesting.
Oh, yeah.
In a standard Linux environment, we might say, great, the file is owned by the auditor, we've set our read-write-execute permissions, job done. We've established discretionary access control, or DAC.
Which is fine for a basic setup.
Right, but this scenario demands something much more rigid. It demands an invisible force field.
You were talking about Linux, security-enhanced Linux.
Yes, I am. Before doing any of this file moving, the administrator actually has to run the command satenforce1. This explicitly forces Linux into enforcing mode.
Right, because standard DSC permissions, the traditional owner, group, and world read-write-execute bits, they are fundamentally flawed for high-security environments.
Because they are discretionary.
Exactly. If a user owns a file, they can accidentally or maliciously change the permissions and expose it. So Linux implements mandatory access control, or MAC,
Right.
and it operates at the kernel level via the Linux Security Modules framework.
I always think of standard DAD permissions, like the physical locks on the cabin doors of a ship. It keeps casual, unauthorized people out of your room.
Right.
But Linux is like the structural bulkheads of a nuclear submarine.
Oh, I like that.
Yeah, even if a door lock is compromised, or an application goes rogue and tries to flood the system, the MAC bulkheads ensure the damage is strictly contained to one specific compartment. The kernel simply will not allow the water to breach the next zone, regardless of who holds the key.
That is a fantastic analogy, because with Linux, every single process, user, and file on the system has a specific security context.
Okay.
To verify that our bulkheads are actually in place around this new error logs file, the scenario has us run ls-lz.
The Z flag being the critical addition there. That reveals the Linux context string rather than just the standard file permissions.
Exactly. And the string we are expecting to see on this file is unconfined_u, object_r, user_home_t, S0.
Okay, let's break that string down, because if you are studying for this exam, you can't just memorize the string, right? You have to know how the kernel is interpreting it.
You absolutely do.
It's a 4-part architecture.
Yes, separated by colons. So the first part, unconfined_u, is the Linux user identity.
And what does unconfined mean in this context?
In this case, unconfined just means the user creating it isn't restricted by a specific Linux user policy, which is pretty typical for standard administrative actions.
Okay, got it.
The second part, object_r, is the role. Files generally just have the role of an object, whereas processes have active roles.
Right. But it's the third part that is the real meat of the security policy, though, the type enforcement.
Yes. User_home_t. This is the most critical part of the string.
Why is that?
This context label proves that the kernel firmly recognizes this file as belonging inside a user's home directory. And why does that matter? Because Linux policies are written around types.
Okay, give me an example.
Well, if a public-facing web server process, which runs under an HTTPD_T type, gets compromised by an attacker, that attacker might try to read our error logs file to find vulnerabilities.
But because our file is labeled user_home_t, the web server process gets blocked.
Completely blocked at the kernel level.
Wow.
The policy strictly dictates that HTTPD_T processes cannot read user_home_T files, even if the attacker manages to elevate to the root user. If the Linux policy denies the interaction between those two types, the access is denied.
That is powerful. And the final part of that string, the S0.
That is the sensitivity level used in multi-level security, or MLS. It dictates the clearance level required to access the file.
So S0 is just the baseline.
Right. S0 is the default baseline level, meaning no special clearance above standard type enforcement is needed. And finally, the scenario requires you to run the getenforce command, which must return the word enforcing,
Proving that the kernel is actively dropping unauthorized requests, not just logging them in permissive mode.
If we connect this to the bigger picture, that strict adherence to mandatory access controls is what separates a hobbyist from an enterprise architect.
You don't just secure the file, you architect the kernel to actively defend the environment surrounding that file.
Well said. But even after establishing that highly sophisticated defense, the system administrator's job isn't finished.
Right. Because a true professional doesn't leave the scaffolding up after the building is finished.
Exactly.
The mission appears complete. I mean, the data is parsed, it's secured under the auditor account, and Linux is actively enforcing the bulkheads. But the final step of the scenario is comprehensive cleanup, or as they call it, zero trace.
This is the operational hygiene phase. The administrator has to forcefully remove the simulated raw access log using arm-F on that TMP raw access log text file.
Okay, that makes sense. Clear the temp file.
But then they go a step further. We completely obliterate the auditor user account we just provisioned by using the command userdel-r auditor.
Now, I have to debate the operational efficiency of this. The -r flag recursively removes the user's home directory and absolutely every file we just carefully parsed and secured inside it.
Deletes everything, yes.
So if this is an enterprise environment where an auditor periodically needs to review parsed logs, why on earth would we burn down the account and the directory? Why not just clear the logs and leave the auditor infrastructure in place for next week?
Because convenience is the ultimate enemy of security.
Really?
In real-world environments, stale accounts are one of the primary vectors for advanced persistent threats, or APTs.
Ah, because nobody is monitoring an account that is only used once a month.
Exactly. An attacker loves a dormant account. If you create a user for a specific, isolated investigation, or even just an automated script, the absolute safest thing to do when the task is over is to destroy the access point entirely.
Leave no trace.
Zero trace isn't just about saving disk space. It is about aggressive attack surface reduction. You cannot hack an account that no longer exists.
So what does this all mean? We started with a wildly chaotic multi-gigabyte data dump. We leveraged the computational efficiency of the C-compiled Regex engine to mathematically isolate the precise anomalies we needed.
Yeah, that grep-e command.
Right. Then we established a secure containment zone using the principle of least privilege. We verified that the kernel-level bulkheads of Linux were actively enforcing our policies. And then, like ghosts, we vanished.
Tearing down the infrastructure to ensure our attack surface remained at absolute zero.
It is a meticulously orchestrated sequence. It demonstrates why system administration is a discipline, not just a series of memorized commands.
It really is an art form.
And for you listening, whether you are actively labbing to pass the RHCSA exam, or you are just managing complex data pipelines in your own engineering role, mastering this specific kind of architecture makes you indispensable.
Absolutely.
It is the ability to filter the noise without crashing the server, and the discipline to adhere to unyielding security protocols even when it's inconvenient.
This raises an important question, though.
Oh, what that?
We've spent this entire deep dive praising the ruthless efficiency of these automated regex filters. But if system administrators rely so heavily on automated scripts to filter data before human eyes ever even see it, what happens to the invisible, unmatched data that gets left behind in the noise?
Well, if the script drops it, it practically doesn't exist.
Precisely. If we are only ever piping out the exact 400 and 500 level errors we already know how to define in our regular expressions, are we potentially automating our own blind spots? Think about it. If a completely novel attack vector generates a bizarre error code that doesn't fit our predefined 40 bracket 0 through 9 pattern, it just gets swallowed by the millions of lines of 200 OK noise.
We might be systematically blinding ourselves to new threats just by only ever searching for the exact historical errors we already know to look for.
It's the paradox of automated security. The tools that make massive scale manageable are the exact same tools that can hide the most dangerous anomalies.
That is a profound point to leave off on. If you only look for what you know, you will never find what you don't. We started out talking about a murky, chaotic digital crime scene, and it turns out the way we so efficiently clean it up might actually be sweeping the most dangerous clues right under the rug.
It's definitely something to think about.
Thank you so much for joining us on this deep dive. Keep examining your raw data, continually check your automated blind spots, and most importantly, keep questioning the systems around you. Catch you next time.